film number 2 about noise in measurement systems. And of course, it's not only in measurement systems, it's in most systems like communication systems, for example, audio systems where you have noise as a problem. And this is about signal to noise ratio, SNR. And it's a quality measure for the signal compared to the noise, and it's often also a requirement in many systems. It's a number that is given in decibels. And why is it given in decibels? Well, let's say that I have a graph here of a yearly salary, and maybe I have like 10k and 100k in Norwegian kroners, NOK. And if I manage to increase from 10k to 100,000k, well, it's just as difficult to increase from 100k to 1 million, and it's just as difficult to go from 1 up to 10 million. So actually, what we have here is a non-linear scale that has been made linear in some way, and we use decibels as a tool to perform that. And it shows that when we use it as a measure for noise in systems, it's given that we can put it down to a linear scale, and that will help us to understand how big the problem really is. Okay, so we have here 3 expressions here. If we measure things in watts, like power, then you have 10 times the log of the fraction there. If it's voltage or current, you have 20 times. Why is it suddenly 20 when it's 10 times when we talk about power? Well, if you heard that yet, power equals V squared over R, or it's I squared times R. And of course, it's also I times V, current times voltage. Well, because of that squared there and there, that's the reason, and together of course with the logarithmic rules, why this is twice as high as the decibel when we measure when we talk about power. So it's 10 times when we talk about power and 20 times when we talk about logs, when we talk about voltage and current. Okay, so what about the other way around? If we have a given decibel of, say, SNR equals 12 decibels, for example, what is then the relation between the powers of a system? So the P signal over P noise is then 10 to the power of 12 decibels divided by 10. And if it was voltage we talked about, voltage signal over voltage noise equals 10 to the power of 12 decibels over 20. So that's the relationship when you turn it the other way around. Examples of decibels, and note here that the increase here is this is a span of about 5 decibels. This is a span of another 5 decibels. Then you have 10 decibels, and then you have 15 decibels, and then to infinity, of course. But still, the relation here is rather linear between the different classes of quality here. And it's definitely not linear if we go back to the equation here, where you see that you have you use the logarithmic function. So this shows that the problem increases in a more or less linear way when we show it as decibels. If we were to show it in a linear scale, that would the problem here would definitely have to be 10 times doubled before we could have a doubled increase in the problem. So, if we have very low signal to noise ratio, 5 to 10 decibels, 5 to 10 decibels means that definitely the signal is still stronger than the noise. So even though we have a stronger signal than noise, even with 10 decibels, it's below the minimum level to establish a connection for a wireless system like this. 10 to 15 decibel, it's the accepted minimum, but that would be rather fragile. 15 to 20, minimum acceptable. This is the minimum possible. And then 25 to 40 decibels, that's a good signal. And over 41 decibels, excellent signal.